Welcome, everyone, to another episode of Behind the Curtain Wall, where we unpack the science, strategy, and real world lessons behind high performance building envelopes. Today, we're taking a deep dive into high rise facade performance. We'll be discussing topics about full scale lab testing to real world storm lessons. Our guest for this episode is Bill Bonner. Bill is the senior glazing consultant and fenestration master in the building and construction division at Intertek. And as always, I'm joined with John Medina, principal consultant at Miami Curtain Wall, bringing decades of building envelope and curtain wall expertise. Bill, thank you for joining us today. Could you give us a quick explanation of what Intertek does and your role there?
My pleasure to be here. I work with Intertek directly as a fenestration master. I'm a certified HAMA inspector and a testing witnesser, and I work at the lab occasionally when I'm working on projects that are being developed. I also help with business development for Intertek in that regard. And I've had numerous years experience. I've got about 42 years in construction, the majority of them in glass and aluminum fenestration. I was a licensed contractor in the state of Florida as a specialty contractor, and so I'm intimately familiar with the workings and logistics of that. But with Intertek, I specifically take that experience to the field for reviews, forensic work, and site inspections and testing.
Excellent. And now to dive into it, would you say the curtain wall testing has changed over the last 30 and 40 years?
Well, Hurricane Andrew introduced itself to South Florida. It introduced an evolution and a very dynamic evolution to the building code. And there were already iterations of building codes over the years that had developed for wind load and not necessarily impact. It came with that code change in 1994. But the entire area of glass and glazing or cladding and building envelope basically changed from that storm on, and that affected everything that has to do with curtain walls, window walls, and any type of facade structure.
And would you say today's systems are more ambitious than what was originally like the original testing standards had anticipated?
Yes, most certainly. They've added features to the testing that although they may have been used, but they were more subdued and they weren't necessarily a statute. Now we're dealing with more statutory requirements for the facade. With the unfortunate circumstance of Champlain Towers, even though that was not what you would call a curtain wall, it had some tall glass in it. And after that collapse, the entire building industry started to look at the building, not just for the structure, but for the skin and how they all perform together and how they connect and how they react together.
Okay. And John, based on your field experience, how have you seen curtain wall testing change over the last 3 and 4 decades?
I think that prior to the Florida Building Code, there was a very vibrant developmental aspect to glazing at laboratories. The testing laboratories that kind of existed back in the 60s was focused on development. People would come up with a design and they would be put through a rigorous process of testing, more so voluntarily. I think Hurricane Andrew for Florida sort of produced a sort of a new direction in glass technology, and the evolution of the glass that we see today has really sort of evolved with, at first just trying to get glass to deal with impact and cycling, a large missile impact, small missile impact. But as a result of sort of the strengthening of the Florida Building Code and understanding that glass breaks, what's come of that is now glass spans of, where before there were very small geometries. Now you have glass that spans 5 to 6 feet by 10 to 12 feet and it can pass very high stringent wind conditions, which is exciting because I think the next generation of glass that we're seeing are these enormous lights of glass, enormous sliding doors, enormous configurations of foldable doors. And I think that that's all as a result of companies like Intertek that, is out there testing, new creative solutions to having indoor, outdoor type of spaces. And so I think that's where the industry is heading as a result of testing laboratories and this notion of glass technology improving to where it is today.
And Bill, have you seen any lab tests reveal something that's completely changed the direction of a project?
The most recent changes are actually dealing with curtain walls and window walls that are located on the first floor in flood-prone areas. We have now flood certification protocol, not just factory mutual, but Intertek has developed its own process of doing that on top of what John had mentioned, which is they've tested for the impact for structural deflection and to and also cycling, which is very much akin to the actual dynamics of a storm. Now we've gotten into flooding, which is also now a byproduct of a surge during a storm. So they are trying to have the properties of these buildings be more resilient to these types of tropical events. And flooding has definitely become a very important feature, along with, as John had mentioned, with the large lights of glass that are in excess of 50 square feet and larger, very large lights of glass. We're looking at different ways to laminate the glass and also to laminate and insulate these huge glass structures, and we test them not only for their ability to resist the structural loads and the aspect ratios and the dynamics of impact. We have also evolved into energy, and the National Fenestration Rating Council is also part of that, which we also cover. We do dynamic testing and also computerized testing on the features that are located at the new glass, which has low emissivity coating. So glass is, I jokingly refer to, is being designed to do everything but make you latte. At this point, there's new features, there's auditory responses and acoustics that are checked with glass, along with the energy and the impact and floods. It's a whole new world. It's not mom and pop's mirror shop anymore. Glass and Glazing has developed through testing and lab testing and R&D from the manufacturers into a real world of science.
I think that from the standpoint of testing and resiliency, I think that it's always an important factor to take into account if a building storefront is at grade or not. If it's at grade, you have to, and you're in a flood zone as per FEMA, you have to take into account that you need to install flood panels or a system that can take on the concussion of a wave that won't flood the building. Right? Can be triple the cost for a building to have a curtain wall that complies with flood. Right? And it just may be a consideration where the client and we have a few of those are capable to afford a storefront that can do that. There may be legal reasons where a federal bank must be open within a period of time unless and it is after a hurricane, people are gonna get in trouble with the federal government because federal banks have to be open within a time period. I want to tell you it's 24 hours to 72 hours, something of that nature. There are reasons to do that. I think that with the projections that there's going to be a seawater rise of 4 or 5 feet by the year 2045, 2050, an interesting consideration if you want to have a building with a life cycle of 100 years to 200 years, that you may want to take that into account at the storefront. I think things that are within our our uh, our scope and that become kind of important now, I think, especially for South Florida, is that there is a flurry of curtain wall assembly buildings that are made up primarily of curtain walls that are following uh, you know, a a huge increase in residential window walls. And so what I'm finding is that suddenly there's a whole lot more curtain going up in Florida where, in the past 15, 20 years since the first boom, there was maybe one or two curtain wall buildings going up. And now all of a sudden, you're West Palm Beach, Fort Lauderdale, Miami Beach, buildings, designers are building for developers skins that are curtain wall, which is very, very unique, very specialized. And there are very few laboratories in the country that know how to test curtain walls. The Florida Building Code doesn't really actually address certain movements and certain things that curtain walls have to deal with that window walls don't, right? And so I think it's a whole lot more fun testing curtain walls than window walls. Window walls are sort of basic. It's kind of the IKEA of design. Everybody kind of seems to know how to do a window wall. Curtain walls are usually require, a much higher specialization by folks that understand glazing assemblies. And interestingly enough, the Florida Building Code doesn't really address serious items and issues that deal with curtain walls. They do deal with large missile impact, small missile impact, air infiltration, water infiltration, certain cycling tests, thermal cycling tests, and things of that nature when you're dealing with insulated lights of glass. But with curtain walls and window walls, it's a little more specialized.
Yeah, the John's right. The state governments, as governments usually do, they're always playing catch up with the R&D that's been thrown out there, unless they're actually doing it themselves, like NASA. But in this instance, the curtain wall has so many more a much broader range of dynamics that can affect it, from interstitial movement, shifting. You can go to California and they do seismic. We haven't really addressed that here because it's not always necessary unless it's been specified to be part of the system. But we test large scale mock-ups for curtain walls all over the country, and in each jurisdiction they all have their own little caveat and peccadillos of how they want that curtain wall tested. In general, they do test for specific structural elements and regarding their embeds and how they're connected, their connectivity to the building, and also how they rotate, if they should go into some sort of movement that would cause a lateral movement or a twist in the framing. And that's just the framing. And then you get into the glass and you have other issues with the glass based on what performance features are you trying to make that curtain wall meet. And in Florida, yeah, we have impact. There have been, large missile impact up to 30 feet, small missile up to, debatable, up to 60 feet. And some people decide they're going to use the same glass all the way through, whether it's large missile or small missile at that point. And then you have the dynamics of the glass in the system. So when we test it, we have we use dynamic 501.1 testing, which is using an airplane motor, or what we call a wolf blower, which is basically an airboat, but on the curtain wall, we are using a radial engine from olden days, airplane engine, and it produces monstrous wind, along with we have spray racks in front of it, and then we have a chamber built out of steel behind it. So we generally go up about, I don't know, 45, 50 feet. Right now, we do precast panels, we do just straight curtain wall. It's something to witness the tests, and generally the manufacturers are involved from the inside. They're in the chamber themselves, looking at it, looking for water and listening for whistling air if it leaks. And it's a sophisticated test, but it's really simple in terms of how it looks. But there's a lot of engineering that goes into making that system meet the dynamics on a larger scale. And John is correct in saying that now we're seeing a lot more of these buildings come to South Florida. And it's also changed the way in which the designers are actually looking at the curtain wall, because there's several types of curtain wall that can be built to go into steel structures or concrete structures. The typical structure down here has been concrete.
What I wanted to tell you, why it makes a big difference, a curtain wall versus a window wall is in an assembly, is that a curtain wall, the way it moves is totally different than that of a window wall.
Correct.
And one of the tests that's required, that should be required in any testing protocol that isn't in a window wall but in a curtain wall, is a inner story movement test. And so what's interesting in the north, Chicago, Boston, New York, building frames are steel. There's and in Florida, our frames are cast in place concrete and or better yet, PT, or a post tension slabs. And why that matters is post-tension slabs and concrete columns, as they cure over time, they shrink, and that's called creep. And so now you have curtain walls, and the reason why curtain wall is called curtain wall is that it hangs on the face of a building. And there's a gap that exists between each unitized panel, and each unitized panel is, say, about 1.5 to 2 stories tall by an entire bay wide. And around that panel, there's a gap. There's a gap so that that panel could move independently of the other panel. That those panels, the typical panel, has to deal with translation, rotation, and racking. Right? Racking means that the panel can slide around from left to right. Translation is that the floors move, so the floor on top and bottom might move in one direction, but the floor in the middle may move in the other direction on a 60-story high-rise. And which is sort of interesting. You have the whole building is moving in a direction, but in between you have panels moving, so that's translation. And then racking is that the corners of the building, they rotate, and each panel has to be able to move. So what's cool about testing in a laboratory is you actually mock up the movements, and you can recreate rotation, right? That, inter-story movements. You can move the panel, move an entire. You could mock up one floor moving in a different direction than the other floor, and then you can see if anything breaks. And what breaks is usually the gasketing. If you get a gasket that breaks, the structure may not fall down, but you could get a lot of water. Up north, if it breaks, you could get a lot of ice and something could blow out. We just get mold and mildew, right? Up north, you have, you collapse, things collapse because ice expands and it causes things to snap and break and so forth. So I think that, the kind of becomes exciting. The basic stuff that we talk about, like dynamic water testing, I used to run those as a young kid at a testing laboratory. I'm fairly deaf as a result of it, having tested so many of those, and being inside these chambers doing dynamic water tests. But what really is sort of exciting to me is seeing how a curtain wall does after thermal cycling, and whether or not the gaskets get brittle when you're testing to 110-degree temperatures, and you drop down to -30 in 3 or 4 cycles, 6 cycles. Well, the gaskets sort of fail when you run some wind pressure, some design pressures, or 1.5 times pressures. How are the gaskets going to do? All right. And when you start separating these joints during interstory movement, what happens? It's a detail, but it's a very important detail, because if those joints collapse, they can't move. Then you start getting buckling of aluminum members and framing members, and it's very hard to replace that on a 60-story. The 42nd story, you have a collapsed joint. It's very hard to fix. The cost is exponential. It's not one to one.
And how much building movement do you realistically expect in a high rise here in Miami?
Significant. If the Empire State Building, where there's no wind on a normal day, can deflect 5 to 6 feet with no wind, then that gives you a pretty good idea of a 60, 90 story in South Florida, where you have regular wind cycles, storm cycles. Every so many years, you're going to get a category 3, 4, 5. So have we really had a category 5 go down Miami Beach or West Palm Beach or Fort Lauderdale? No, we haven't. I think Hurricane Andrew at first was categorized as they said it was a category 1, and then it got moved up to category 3. The Miami Herald had written that sustained winds which they were wrong at the time, said sustained winds of 200 miles per hour. If they would have had sustained winds at 200 miles per hour, they would have washed the entire Miami Beach away. I think that there may have been gusts of 200 miles per hour, but not sustained winds. And a sustained wind is a minute long. It's literally one entire minute of a wind at 200 miles an hour. And that's clocked at 30 feet above grade. So that kind of gives you an idea. You try to 200 miles an hour. You know what it feels like when you're driving your car at 80. It's pretty scary. So that kind of gives you an idea. And by the way, a category 5, you can't really truly measure category 5 winds. They're just just enormous.
So, what would be real world consequences from ignoring this kind of building drift in those kinds of scenarios?
Right now, we are. We actually are. We don't have the testing that is being done based on the categories that John was talking about. I was going to add to his point about Hurricane Andrew. When Katrina came in Fort Lauderdale, it was a Cat 1, and it made a left turn and went straight down the beach to Miami Beach and downtown Miami, and it was a Cat 1. So you're looking at, 80 miles an hour, 85 mile an hour
85
sustained winds. And what happened is it literally sucked the glass out of many buildings downtown Fort Lauderdale. The Department of Education was absolutely effaced. The curtain wall was ripped off the building at 85 miles an hour. So I wouldn't even want to discuss the potential or what would happen if there was a Cat 5 like Hurricane Irma a few years back. I think it was 2017, was aimed at the path was going to go straight through the Florida, starting at Miami, just going right through the center of the state. And I'd never seen so many cars on the highway in my life. And I evacuated 4 days before it hit, because they made it mandatory for the Keys. And I've never been going a straight line at 85 miles an hour, bumper to bumper, from here to Jacksonville like it did. So the winds in a big storm like that were really untested. And I've talked to general contractors over the years, and I just shake my head. I want to say curtain walls are good. They're big. They perform, but we don't know how they're going to really perform, as John said, because of the 3 different types of movement. And then also what would happen, even as the code has relaxed or did relax enough to where it allowed for a safety factor using wind tunnel studies. They've got all these buildings jammed together in tight corridors. And what happens is when you it's like trying to shove, 10 pounds of something in a 1 pound hole. What happens is the wind velocities get more dense, and the Venturi effect at each corner gets more intense. So I hate to say it, but I see trouble, and I I don't
So
think we were
one of the
planned
things
for it.
one of the things that the laboratory does, so when you're looking at the wind tunnel study, they take into account the structural implications of the frame of the building, and they apply that to the curtain wall, and then from there they connect. They would literally extrapolate what the wind pressures are on the curtain walls, and there's a factor. And I want to tell you, is like a factor of 4 is usually the rule of thumb, but the factor that's taken into account is that the curtain wall in everyday use should sustain most of the higher pressures, and there'll be some damage to be expected. The objective of curtain walling and window walling is to prevent the hull of the ship from creating sufficiently large crease or opening that would it would take out the utilities of the building. That's the objective. If you knock out the utilities of the building, the ship is sunk, right? The it's like the Titanic. You breach the hull and you're done. So the strategy is a curtain wall that will remain in place, take a beating from a small missile impact, large missile impact, in the bottom 20, 30, 40 feet. Those are the palms that become missiles, debris, whatever wood construction materials, and so forth. So that's large missile impact. Small missile impact are all those items, satellite dishes that become frisbees, right? They just keep flying in the air and they keep bumping into everything up, 200, 300, 400, 500 feet up in the air. Sections of buildings fly off from one building, hit the other building. You discover, buildings that are 2 or 3 blocks away, and you'll find all of their stucco and barrel tile in somebody's unit, 500, 600 feet up in the air. And you discover all of these interesting artifacts. So you discover your neighbors had something to do why your building is all the glass is cracked up. But one of the things that's interesting is that as those winds become greater in a hurricane like Andrew, you get these microbursts, which are like these little mini tornadoes, and they happen in the most random of places. Right? You can't predict it. You don't know what that wind speed is because it's this little microburst. And I had heard of that, I had read of that, but I hadn't seen it until one of the hurricanes back in like '85. I want to tell you it was Wilma. This one building that I was responsible to open, which I'm not going to mention, had $46 million of damaged glass. And it was damaged mostly because all the other buildings' ballast wound up in our building. The first time the building's glazing was installed, it cost $23 million. Once there was like 17,000 lights of glass that broke, and it was $46 million. But what's remarkable about the failure is that the skin cracked up, but it never got to the utilities. So within 3 days, we were able to reopen the building, and then we spent the next 3 to 4 years fixing it. That's how it's supposed to work. It was a fortune, $46 million. I'm sure the 7 layers of insurance weren't too happy that they had to spend $46 million, but it went to 7 layers of insurance covering that one very prestigious building on Brickell. So I think that when at the laboratory, we're able to prove that at the higher pressures, stuff is going to break. The objective is that it stays together long enough that it gets past the hurricane, which usually the cycle of the hurricane, a real large hurricane is fast moving. It doesn't just necessarily sit there forever, but you could have hurricanes that are there for 2 or 3 days and you get a lot of water, right? But the category, we haven't really seen a true category 5. I went through 2 category 5s when I was a little kid in the 60s. Ever since I've measured hurricanes based on those 2. So I got a sense of it. And at a laboratory, you could kind of get the sensation of what happens when you're testing, at 150 mile per hour, 200 mile per hour, 210, 220. And it's a lot of fun to witness when things start to fall apart. It's kind of, you're like the thrill seeker in you that doesn't have to chase hurricanes. You could see it at Intertek, witness it.
There are companies, manufacturers that will oftentimes set a benchmark for what they want that product to meet, and then they will direct the lab to go to destruct and see how far, how much of a licking can this take, and it's amazing. And John's right. I mean, it's like you're in a 2-year-old's toy box just throwing stuff around, and there's some excitement to it, of course, with the velocity of wind and pressure and the noise, all of it together. It's calamitous, but at the same time, it's exciting to see, because some of these systems can attain some very, very high structural loading, and it's sometimes it's good to see how far you can go with it and see how long it will last under true duress. So you were going to ask.
And you guys mentioned the project that you're both going to be working on soon, which is, a pretty big one in South Florida and Brickell. Obviously, once this one takes off, it feels like this is more of a pioneer stage for a project this big. Obviously, after pioneers, we see a lot more buildings adopt the same size or even bigger. Do you see in the future of testing, do you see, you know, plants have to be bigger, labs have to accommodate to these, and how do you see that happening?
No, I think the I've already seen large modules, from around the world, especially when I worked at construction research and we had spoken to George, and we had done a session with George over at construction research. For the most part, you could build fairly large mock-ups that are very tall, 45, 50 feet, and then very wide. I don't think that the facilities have to become any larger. You just, depending on what you're trying to accomplish, you just build smaller mock-ups, and then you can visualize them coming together. Unitized curtain walls, there are a variety of methodologies that putting cladding that works with glazing and all kinds of systems to shield or to cause water to run off of them. Pressure equalize, rain screen systems. That all of those can be tested in laboratories like Intertek or construction research. And that's the other that sort of a founding partner in testing. Those laboratories have the ability to build large mock-ups. I think it's the experience of people in the industry. They're likely a handful of designers, people that design curtain walls, right? That each building is somewhat unique, but different. And it's finding the right curtain wall guy and his office that sort of inputs in the design, the physical design of by the manufacturer that can build a great deal of the wave of the future type of assemblies. So, for instance, carbon fiber cladding that becomes, somewhat rounded, modernized stuff that aluminum can't do, but that looks very plastic like. Really exciting proposition, can resist a great deal of wind load and pressure. But, how does it does in regards to fire? You know, you have a tall building. Do you want something that looks sort of plasticky, melting? So there's, I think that there's the future designs when you look at these images of what buildings are going to look like in Gaza, for example. They always make them look very, very sort of organic, sustainability like, with all of these curves and features that seem really exciting. Well, aluminum doesn't like to do that. And most curtain walls that we know are glass and aluminum. Once you start talking about creating very curvy, arched like configurations, and you start incorporating carbon fiber, there may have to be a need to test in situ, not in situ, but in the laboratory for all of the things we've talked about, including fire, instead of a UL laboratory like up in Canada. Test that as part of the package. But carbon fiber is not something that you readily see in Florida. That you're starting to see people talk about it, and then someone like me or Bill has to say, "Well, wait a minute, that's not aluminum. It's not gold. It's not steel. Well, how's it going to do when not only are you having a hurricane, but potentially a fire? Because you can't have a fire during a hurricane, right? So you remember that terrible nuclear explosion where a tsunami hit and at the same time they had a fire. You know, it's one of those topics of how many disasters can happen all at once. You could
Right.
have a seismic, you could have a fire, and then you could have a hurricane. It's like how many things can go wrong at the same time. So, we're getting these buildings that are going to be 1,000 linear feet tall, right? Or we have a building that maybe in 5 or 6 years from now, king tide, you'll eventually have water in your lobby if you don't have flood proof panels. How many disasters can you have at one time? And the laboratory, a full-scale laboratory like Intertek, makes an effort to see how all these things work at the same time. Are you going to have a short circuit somewhere, and you're not going to be able to deal with something? I remember a mock-up I was involved in, which was for Japan, somewhere in Japan. I don't remember exactly, and we tested for hurricane and tsunami, a hurricane event that was a tsunami under pressure. So the chamber was tested at sustained winds of like 70 plus miles an hour. And at the same time, it wasn't supposed to leak. And it was a pretty remarkable thing being inside of this chamber with 70 psf pressure and watching the gutters work and removing all of the water that was going into this thing. So I think that people speak about what's going to happen in the environment. And laboratories, can adapt to test worst case scenarios. And it's something that Intertek can do as long as the the owner's specification, what the owner's expectations are, right? The owner's expectations become very important because you could, for the most part, make glass bomb proof, but the cost has to be picked up by the owner, right? And so you can test for that, just that it's going to cost what it costs.
Well, John touched on the multiple facets that glass has to be tested for. So what happens is that when the designers come up with an idea, then it's up to the labs to innovate to provide the backbone for testing that product. You mentioned bomb blast. I've dealt with bomb blast films and bomb blast curtain walls and arena testing. That's one we didn't touch on earlier in the conversation. But I think curtain wall is essentially going to end up being looked at as obviously the building envelope, the epidermis of the building, and whatever features that can be literally thought up about what it can resist, how long can it resist it, and will it survive? Those are all going to be tenets of what the lab is going to have to innovate in order to produce mock-ups that can assimilate the products properly that can perform those functions.
Excellent. Well, I think that just about does it for the time for today. Bill, John, thank you for sharing the insights as always and your experience with us today. I think conversations like these are what help raise the standard in our industry. And to our
Thank
listeners, thank you for joining us on another episode of Behind the Curtain Wall. We'll see you on the next one.